Hello friends, in the previous lecture we learnt the second law of thermodynamics, which states that processes occur in a certain direction, not in any direction. A process does not occur unless it satisfies both the first and the second law of thermodynamics, and lastly we discussed that work can be converted to heat directly, but heat can be converted to work only by some devices called heat engines. In today's lecture, we shall be discussing the Kelvin-Planck statement and Clausius statement about second law of thermodynamics, refrigeration, heat pumps and the perpetual motion machines. The second law of thermodynamics, Kelvin-Planck statement. We have in our earlier lecture shown that even under ideal conditions, a heat engine must reject some heat to a low temperature reservoir in order to complete the cycle. That is, no heat engine can convert all the heat it receives to useful work. This limitation on the thermal efficiency of heat engines forms the basis for Kelvin-Planck statement of the second law of thermodynamics, which is expressed as: it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. That is, a heat engine must exchange heat with a low temperature sink as well as a high temperature source to keep operating. The Kelvin-Planck statement can also be expressed as: no heat engine can have a thermal efficiency of 100%, or as for a power plant to operate, the working fluid must exchange heat with the environment as well as with the furnace. Note that the impossibility of having a 100% efficient heat engine is not due to friction or other dissipative effects. It is a limitation that applies to both the idealized and the actual heat engine. Refrigerators. We all know from experience that heat is transferred in the direction of decreasing temperature, that is, from high temperature mediums to low temperature ones. This heat transfer process occurs in nature without requiring any devices. The reverse process, however, cannot occur by itself. The transfer of heat from a low temperature medium to a high temperature one requires special devices called refrigerators. Refrigerators, like heat engines, are cyclic devices. The working fluid used in the refrigeration cycle is called a refrigerant. The most frequently used refrigeration cycle is the vapor compression refrigeration cycle, which involves four main components: a compressor, a condenser, an expansion valve and an evaporator. The refrigerant enters the compressor as a vapor and is compressed to the condenser pressure. It leaves the compressor at a relatively high temperature and cools down and condenses as it flows through the coils of the condenser by rejecting heat to the surrounding medium. It then enters a capillary tube where its pressure and temperature drop drastically due to the throttling effect. The low temperature refrigerant then enters the evaporator, where it evaporates by absorbing heat from the refrigerated space. The cycle is completed as the refrigerant leaves the evaporator and re-enters the compressor. In a household refrigerator, the freezer compartment where heat is absorbed by the refrigerant serves as the evaporator, and the coils, usually behind the refrigerator where heat is dissipated to the kitchen air, serves as the condenser. A refrigerator is shown here schematically. Here QL is the magnitude of the heat removed from the refrigerated space at temperature TL. QH is the magnitude of the heat rejected to the warm environment at temperature Th, and W net in is the net work input to the refrigerator. As discussed before, QL and QH represent magnitudes and thus are positive quantities. Coefficient of performance. The efficiency of a refrigerator is expressed in terms of the coefficient of performance, denoted by COPR. The objective of a refrigerator is to remove heat, that is QL, from the refrigerated space. To accomplish this objective, it requires a work input of W net in. Then the COP of a refrigerator can be expressed as desired output divided by required input and is equal to QL upon W net in. This relation can also be expressed in rate form by replacing QL by Q dot L and W net in by W dot net dot in. The conservation of energy principle for a cyclic device requires that W net in is equal to QH minus QL. Then coefficient of performance relation becomes COPR is equal to QL upon QH minus QL and is equal to 1 upon QH by QL minus 1. Notice that the value of COPR can be greater than unity, that is, the amount of heat removed from the refrigerated space can be greater than the amount of work input. This is in contrast to the thermal efficiency, which can never be greater than 1. In fact, one reason for expressing the efficiency of a refrigerator by another term, that is, the coefficient of performance, is the desire to avoid the oddity of having efficiencies greater than unity. Heat pumps. Another device that transfers heat from a low temperature medium to a high temperature one is the heat pump. Refrigerators and heat pumps operate on the same cycle but differ in their objectives. The objective of a refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. Discharging this heat to a higher temperature medium is merely a necessary part of the operation, not the purpose. The objective of heat pump, however, is to maintain a heated space at high temperature. This is accomplished by absorbing heat from a low temperature source such as well water or cooled outside air in winter and supplying this heat to a high temperature medium such as a house. The measure of performance of heat pump is also expressed in terms of the coefficient of performance and is defined as desired output over required input and is equal to QH upon W net in, which can also be expressed as COP-HP is equal to QH upon QH minus QL and is equal to 1 upon 1 minus QL upon QH. The comparison of coefficients of performance of refrigerator and the heat pump reveals that COP-HP is equal to COPR plus 1 for a fixed value of QL and QH. This relation implies that the coefficient of performance of a heat pump is always greater than unity, since COPR is a positive quantity. That is, a heat pump will function at worst as a resistance heater, supplying as much energy to the house as it consumes. In reality, however, part of QH is lost to the outside air through piping and other devices, and COP-HP may drop below unity when the outside air temperature is too low. When this happens, the system usually switches to a resistance heating mode. most heat pumps in operation today have a seasonally averaged COP of 2 to 3. Most existing heat pumps use the cold outside air as the heat source in winter, and they are referred to as air source heat pumps. The COP of heat pumps is about 3 at design condition. Air source heat pumps are not appropriate for cold climates since their efficiency drops considerably when temperatures are below the freezing point. In such cases, geothermal heat pumps that use the ground as the heat source can be used. Geothermal heat pumps require the concealing of pipes in the ground 1 to 2 meter deep. Such heat pumps are more expensive to install, but they are also more efficient, up to 45% more efficient than air source heat pumps. The COP of ground source heat pumps is about 4. Air conditioners. They are basically refrigerators whose refrigerated space is a room or a building instead of the food compartment. A window air conditioning unit cools a room by absorbing heat from the room air and discharging it to the outside. The same air conditioning unit can be used as a heat pump in winter by installing it backwards. In this mode, the unit absorbs heat from the cold outside and delivers it to the room. Air conditioning systems that are equipped with proper controls and a reversing valve operate as air conditioners in summers and as heat pumps in winters. The second law of thermodynamics, Clausius statement. The second classical statement of the second law, which is related to refrigerators or heat pumps, is the Clausius statement and is expressed as: it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. It is a common knowledge that heat does not, of its own violation, transfer from a cold medium to a warmer one. The Clausius statement does not imply that a cyclic device that transfers heat from a cold medium to a warmer one is impossible to construct. In fact, this is precisely what a common household refrigerator does. It simply states that a refrigerator cannot operate unless its compressor is driven by an external power source such as an electric motor. This way, the net effect on the surroundings involves the consumption of some energy in the form of work, in addition to the transfer of heat from a colder body to a warmer one. That is, it leaves a trace in the surroundings. Therefore, a household refrigerator is in complete compliance with the Clausius statement of the second law. Both the Kelvin-Planck and the Clausius statements of the second law are negative statements, and a negative statement cannot be proved. Like any other physical law, the second law of thermodynamics is based on experimental observations. To date, no experiment has been conducted that contradicts the second law, and this should be taken as sufficient proof of its validity. Perpetual motion machines. We have repeatedly stated that a process cannot take place unless it satisfies both the first and second law of thermodynamics. Any device that violates either law is called a perpetual motion machine, and despite numerous attempts, no perpetual motion machine is known to have worked. But this has not stopped inventors from trying to create new ones. A device that violates the first law of thermodynamics is called a perpetual motion machine of the first kind, and a device that violates the second law of thermodynamics is called a perpetual motion machine of the second kind. Consider the steam power plant as shown. It is proposed to heat the system by resistance heaters placed inside the boiler instead of by the energy supplied from fossil or nuclear fuels. Part of the electricity generated by the plant is to be used to power the resistors as well as the pump. The rest of the electric energy is to be supplied to the electric network as the network output. The inventor claims that once the system is started, this power plant will produce electricity indefinitely without requiring any energy input from the outside. Well, here is an invention that could solve the world's energy problem if it works, of course. A careful examination of this invention reveals that the system enclosed by the shaded area is continuously supplying energy to the outside at a rate of Q dot out plus W dot net out without receiving any energy. That is, this system is creating energy at a rate of Q dot out plus W dot net out, which is clearly a violation of the first law. Therefore, this wonderful device is nothing more than a perpetual motion machine 1 and does not warrant any further consideration. Now, let us consider another novel idea by the same inventor. Convinced that energy cannot be created, the inventor suggested the following modifications that will greatly improve the thermal efficiency of that power plant without violating the first law. Aware that more than half of the heat transferred to the steam in the furnace is discarded in the condenser to the environment, the inventor suggests getting rid of this wasteful component and sending the steam to the pump as soon as it leaves the turbine as shown in this figure. This way, all the heat transferred to the steam in the boiler will be converted to work, and thus the power plant will have a theoretical efficiency of 100%. The inventor realizes that same heat losses and friction between the moving components are unavoidable and that these effects will hurt the efficiency somewhat, but still expects the efficiency to be no less than 80% for a carefully designed system. Well, the possibility of doubling the efficiency would certainly be very tempting to plant managers, and if not properly trained, they would probably give this idea a chance, since intuitively they see nothing wrong with it. But a student of thermodynamics will immediately label this device as a perpetual motion machine too, since it works on a cycle and does a net amount of work while exchanging heat with a single reservoir only. It satisfies the first law, but violates the second law, and therefore it will not work. Countless perpetual motion machines have been proposed throughout history, and many more are being proposed. Some proposers have even gone so far as to patent their inventions, only to find out that what they actually have in their hands is a worthless piece of paper. So friends, here we come to the end of our discussion, and therefore we sum up. Refrigerators and heat pumps are devices that absorb heat from low temperature media and reject it to a higher temperature ones. The performance of a refrigerator or a heat pump is expressed in terms of the coefficient of performance. The Kelvin-Planck statement of the second law of thermodynamics states that no heat engine can produce a net amount of work while exchanging heat with a single reservoir only. The Clausius statement of the second law states that no device can transfer heat from a cooler body to a warmer one without leaving an effect on the surroundings. Any device that violates the first or the second law of thermodynamics is called a perpetual motion machine. So that is it for today. In the next lecture, we shall be discussing reversible and irreversible processes and the Carnot cycle. Thank you very much.